Ever find yourself scrolling through social media and get that little voice in the back of your head wondering how those algorithms really pick what to show you?
It's a question a lot of people have, especially now, with all the talk about AI being used everywhere.
Right. Like how much is just pattern matching and how much is actually, I don't know, closer to how we think?
It's a question researchers are grappling with, too,
Yeah.
especially as AI systems get more complex. Can they really handle information that's not just, words on a page?
That's what I find so fascinating about the research we're diving into today. It throws AI into the world of, get this, graphs.
And no, not the kind you doodled in your math notebook.
Though maybe they're not as different as you'd think.
You got it. We're talking about the underlying structure of things we encounter every day. Social networks, online maps, even how information flows on the internet. Think nodes for each data point, and edges for the connections between them. This research wants to see if AI can understand those connections, not just recognize patterns.
Okay, I'm hooked, but walk me through it. How do they even begin to test something like that?
So picture this. Researchers gave these large language models, the LLMs everyone's talking about, a pop quiz.
Okay, a pop quiz about graphs.
Exactly. They used 10 different graph problems,
Right.
and they varied the difficulty. Some were more straightforward, like how many total nodes are in this graph?
Nice, simple enough, right?
Right. But then they stepped it up a notch, throwing in things like finding the minimum spanning tree, which, believe me, gets pretty complex.
Time out. I think we might have lost some folks back there with the minimum spanning tree. Can you break that down for us?
Imagine you're building roads to connect a bunch of towns. You want to use the least amount of road possible, but still be able to drive from any town to any other town. That's essentially what the AI had to figure out.
Okay, that makes more sense. So finding the most efficient route, that was the challenge.
Exactly. And to make it even tougher, they tested the LLMs on small, medium, and large graphs. So we're talking about increasingly complex structures.
All right, so we've got our AI test subjects and a set of brain-bending graph challenges. But how do you even explain a graph problem to AI? Do they, get a diagram or something?
Not quite. I mean, think about it. We're trying to see if AI can process information in a way similar to us.
Okay.
And we don't just think in pictures, right?
True enough. So how do they tell the AI what to do?
That's where prompting comes in.
All right, hit us with what is prompting?
Think of it like giving someone clues to solve a riddle.
I like riddles. Lay it on me.
Okay, so the researchers used different prompting methods. First, there was the zero-shot approach, where the AI gets 0 examples beforehand, just the task instructions.
Talk about tough love. Just thrown right into the deep end.
Right. Then they tried one shot, where they gave one example to show the AI what to do. So here's a graph with X number of edges. Now tell us how many edges this graph has.
Ah, so a bit of a helping hand.
Exactly. A little I do, we do, to get the AI warmed up.
And did they try any other prompting styles?
Yeah. They experimented with actually prompting the AI to think step by step, which I thought was really cool.
Interesting. So trying to nudge it towards a more human-like thought process.
Right. But here's where it gets really wild. They also tried giving the AI pseudocode as part of the prompt.
Pseudo what now?
Pseudocode. It sounds more intimidating than it is. Think of it like a simplified set of instructions for how to solve a problem. Kind of like a recipe for an algorithm, but easier to understand than complex programming language.
So we're essentially giving the AI a cheat sheet.
That's a fantastic question, and it gets right to the heart of what makes this research so intriguing. It's not really about handing AI the answer. It's about seeing if providing that structured way of thinking, like a programmer might use, can help it learn. Can it go beyond just mimicking human language and actually mirror how we problem solve?
Okay, my mind is already buzzing, and we haven't even gotten to the results yet. We've got our graph problems, our AI test subjects, and all these different ways of explaining the task. What happens next?
This is where it gets really interesting. The findings reveal some really surprising things about both the capabilities and limitations of these LLMs.
All right, so the stage is set. We've got our graph problems, our different prompting methods. What were the researchers hoping to learn from all of this?
They were really interested in seeing how these LLMs, these large language models, how they handled information that got more and more complex.
And of course, whether giving them a little help, like with that pseudocode, changed how well they could learn, right?
Exactly, and the results were intriguing, to say the least.
Hit me with the good stuff. What did they find?
Okay, so they tested 2 main LLMs. One, GPT 3.5, you've probably heard of.
Oh, yeah, that's the big name in LLMs right now, isn't it?
It's considered one of the most advanced out there, yeah. And then they also used Mixtral.
Mixed that one rings a bell, but I'm not as familiar.
It's open source and considered a bit less powerful than GPT 3.5, at least, based on its specs.
Okay, so we've got a bit of a David and Goliath situation going on here. How did they do? Did Mixtral hold its own?
You might be surprised, both LLMs actually aced the basic tasks,
Like what? Give me an example.
like counting the total number of nodes, even on those really massive graphs they tested.
No problem for them, huh?
Nope. Which suggests that these models, they have some inherent capacity for this kind of reasoning.
That's pretty impressive. But it could have been all smooth sailing. What about the tougher challenges, the ones that really make your brain sweat a little?
Yeah, that's where we start to see some limitations. So remember how they both did great with counting nodes, even on those large graphs?
Yeah, superstars.
Well, when it came to counting edges on the large graphs, both struggled.
Hold on, back up a sec. Why would counting edges be harder than nodes? Aren't they both just like parts of the graph?
That's a great question. And it highlights how these LLMs, how they approach these problems. It's different from how we might, edges represent relationships, right?
Yeah, the connections between the data points.
Yeah. So as a graph gets bigger, the number of potential connections, it explodes. It's possible the LLMs, they just got overwhelmed by the sheer volume of relationships, even in a task that seems pretty simple to us.
So even these super advanced AI systems, they have their limits. Which makes you wonder, did that pseudocode prompting actually make a difference? Did it help them overcome those limitations?
And that's the million-dollar question, right? For Mixed-Roll, it was like night and day. The pseudocode significantly boosted how well it did on the tougher tasks, like finding the shortest path or figuring out the connected components in a graph.
Okay, before we get too far, remind me again, what are connected components?
Imagine you've got a big network, right? Connected components, those are like the separate groups within that network where every point within a group is connected, but there's no path between the groups.
Okay, like separate friend circles within a larger social network. You can't get from one to the other without some kind of introduction.
Perfect analogy. And Mixtral, with that pseudocode, it was able to handle those kinds of tasks much more effectively.
Our AI underdog is pulling ahead. What about GPT 3.5, our heavyweight champion? Did the pseudocode give it an extra edge, or was it already performing at the top of its game?
It wasn't as dramatic a change as with Mixtral, but even GPT 3.5, it showed some improvement with pseudocode, especially in specific situations.
That's huge, though. Even the most powerful LLMs, they can still benefit from a more structured approach to problem solving, right?
Yeah.
Like, it's not just about the raw data, it's also about being able to organize all that information in a way that makes sense.
Exactly. And it kind of challenges our assumptions about AI, Maybe it's not enough to just feed them more and more data. Maybe we need to get better at guiding their thought processes if we want them to really excel.
This is where it gets really exciting for me, because it's not just about AI acing tests. It's about understanding how they think and using that knowledge to solve real-world problems, right?
Absolutely. This research, it opens up a ton of possibilities. But before we get too far ahead of ourselves, I'm curious, what's really stood out to you so far about these results? Any big aha moments?
I gotta say, the fact that pseudocode actually moved the needle, especially for mixed draw, that really surprised me.
Yeah, it challenges what we think we know about how AI learns, right?
Yeah.
Like maybe more data isn't always the answer.
Right. It's like we're getting a glimpse of AI that could think more strategically, more like we do.
And that opens up so many possibilities for using AI to tackle real-world problems.
Okay, you can't just drop a whole new world on me and not elaborate. What kind of real-world applications are we talking about here?
Well, imagine taking these insights and applying them to, say, healthcare. AI could analyze all sorts of complex medical data, things like patient histories, genetic information.
And because of this research, it could actually understand the relationships between all those different data points, right?
Exactly. It could be like giving doctors an AI-powered magnifying glass, helping them see patterns and connections they might otherwise miss.
That's incredible. It could revolutionize how we diagnose and treat diseases. What other fields could benefit?
Oh, the possibilities are practically endless. Finance, for example. AI could analyze market trends, global economic indicators, all while understanding the interconnected risks and opportunities.
We could make smarter investments, avoid financial crises.
Exactly. And this is just scratching the surface. Remember how we talked about different types of graphs? Well, this research, it focused on randomly generated ones. But real-world networks, they're rarely random, are they?
That's right. You mentioned social networks earlier. Those are anything but random.
Exactly. Imagine the complexity of a social network.
Yeah.
Every person is a node. each relationship an edge. It's not just that people are connected, it's the history, the nuances, all those overlapping circles of influence.
It'd be like trying to figure out all the unwritten rules of a party just by looking at a guest list.
Exactly. And that complexity, it's everywhere. Think about a graph representing the internet itself. Websites are nodes, links are edges. It's mind-bogglingly huge.
And understanding how information moves through that network, how ideas spread, that feels like the ultimate AI puzzle.
It really does.
Yeah.
Can AI not just map out these networks, but truly understand the meaning behind those connections? That's the question, isn't it?
It's a question with huge implications. What a deep dive this has been. We've gone from the nitty-gritty of graph theory to the future of AI.
It's an exciting time to be paying attention to this stuff, that's for sure.
It really is, and we want to keep the conversation going. So listeners, we want to hear from you. What are your thoughts on all of this? Does it change how you view AI? What excites you? What worries you? Head over to our website, find us on social media, let's discuss. And until next time, stay curious, everyone.